Today we're going to be solving exponential and logarithmic equations using some of the properties that we've already looked at in the last couple sections. So let's first recall the following properties, one-to-one properties and inverse properties for these exponential and logarithmic equations. So for my one-to-one properties, a to the x equals a to the y if and only if x equals y. Well, that makes sense. If I've got a to some power equals a to some other power, since it's the same base, it must be true that they've got the same powers. Okay, well, log base a of x equals log base a of y if and only if x equals y. Again, if I've got the logarithm of some base, and this is going to be equal to the logarithm of some other base, okay, taking a log of x equals log of y, it must be true that x equals y because these are the same logarithms. And now my inverse properties, if I've got a to the power of log base a of x, then this base here, a, is going to cancel out with this log base a, leaving just an x. So that's going to undo each other. Those are going to undo each other, leaving just an x here. And the same is true going the other way. If I've got log base a of a to the x, well, log base a of a, those things are going to undo each other, leaving just whatever's in that power, x. In other words, let's take a look here. It says to solve exponential equations, take the logarithm of both sides. So solve e to the x equals 72, or in other words, e to what power equals 72. And if you were to bring over your calculator, you could try a couple of different things. You could say e to the second power. Nope, that's not even close to 72. E to the third power. We're getting closer. E to the fourth power. Okay. E to the fifth power. Now I know it's between 4 and 5. And we'd have to go, well, what about 4.5? Getting closer, but it would take us a long time to try and figure out what is this exponent that's missing. So we've got to come up with some other methods of finding what this x is supposed to be. And what I'm going to do is I'm going to use some of the properties that we just talked about. I know that this base of this exponent is e. So if I take a logarithm base e of both sides, then I can undo this e that's happening here, leaving just an x. In other words, I'm going to do, since this is base e, the natural log of e to the x. But if I do that, then I've got to do the natural log of 72. Well, the natural log and e here, these will undo each other, leaving just x equals the natural log of 72. So I can go back into my calculator, and instead of trying to guess and check for x in e to the x, I can now just find what is the natural log of 72. And it's roughly 4.28. We'll round that 7 up because of the 6. So x is roughly 4.28. And just to show you this works, I can go back in here and I can say, what is e to the 4.28? And it should be really, really close to 72. Now we rounded a little bit, so it's not going to be 72 exactly, but e to the 4.28 is indeed really close to 72, 72.24. We're just off a little bit because we rounded. All right, next one. What about this? Solve 3 times 2 to the x equals 42. Okay, so what I want to do is I want to isolate this 2 to the x. So I'm going to divide both sides by 3. When I divide both sides by 3, 3 is here, we'll divide out. leaving 2 to the x is equal to 42 divided by 3. Well, that's going to be 14. All right, now I've got this 2 to the x. My base here is 2. So what I'm going to do is I'm going to take the logarithm of both sides base 2. So log base 2 of 2 to the x is going to be equal to log base 2 of 14. So this log base 2 and this 2 will undo each other, leaving just an x. But the problem here is log base 2 of 14 isn't something that I can put into my calculator. At least it's not something I can put into my calculator as it is. What I need to do is a change of base formula. So I'm going to have x equals the log base 2 of 14. And then over here, I'm going to say x is equal to, since I can't put this into my calculator as it is, we're going to change the base to log base 10 of 14 over log base 10 of my old base is 2. This is something I can put into my calculator and find what x is. X is equal to, let's bring this back over, log base 10 of 14 over log base 10 of 2. Remember that your calculator might not show you the base 10 here. It's assuming the common base, so it's assuming log base 10. So this is 3.807. We'll round that to 3.81. So x is roughly 3.81. And again, to check your answer, you can take this 3.81, you can plug it into your original equation here, 3 times 2 to the 3.81, and you should get something very close to 42. Remember that we're rounding a little bit, so we might be off by just a tiny bit there. Okay, so that takes care of starting with an exponent and trying to find what my missing exponent here is. What about problems like this where I've got a logarithm? Well, to solve a logarithmic equation, we're going to do something called exponentiation. We're going to exponentiate both sides. In other words, take both sides to some power here. So let's say I've got the natural log of 3 to the x equals 2. Now the natural log is base e. So to get rid of this natural log and make it so it's just this 3x on the inside here, I'm going to say e to this power is going to be equal to e to the right side is just 2. So let's see what that looks like. E to the natural log of 3x is going to be equal to e to the second power. What I do to one side, I've got to do to the other side. Now on this left side though, e to the log base e, or natural log, undoes each other, leaving just 3x equals e to the second power. Now, I want to solve for x, so I've got to divide both sides by 3 here. So don't plug in your e squared or e to the second power in just yet. We're going to wait till the end. Divide both sides by 3. And we'll get x equals e squared over 3. So x is roughly, okay, let's plug that in and find out. The top part is going to be e squared. Second part is going to be 3. So e to the second power over 3 is about 2.46. So x is about 2.46. All right. Lastly here, I've got log base 3 of 5x minus 1 equals log base 3 of x plus 7. Okay, well, I notice that the left side here, the right side here, these are both logarithms of base 3. And if they're both the same base here, log base 3 of this equals log base 3 of that, it must be true that this equals that, or 5x minus 1 equals x plus 7. So I can go ahead and I can just get rid of these log base 3's. So 5x minus 1 equals x plus 7 here. And we're going to subtract x from both sides. That's going to make 4x minus 1 is equal to 7. You can add 1 to both sides. Four x is going to be equal to 8 here. And then finally, divide both sides by 4. So we'll get x equals 2. All right, so this is great and all, but how could we use this outside of just doing random, logarithms and exponents? What's an application for this? Well, how about this? Let's say you've deposited $500 in an account and it pays 6.75% interest. That's pretty good interest. It compounded continuously. How long will it take your money to double? So we did a little bit of compound interest in the last section here. Since we're compounding continuously, it says hint, we're going to be using this. A equals PERT, our principal, times e to the RT, where R is our rate and T is time in years. All right, so let's actually just write this down. A equals PERT. And let's see what we know. All right, A is the value of the account after however much time. Now, it's not directly told to us, but it does say we're depositing $500 and we want to know when it's going to double. So double $500 would be 1,000. A equals 1,000. P is my principal amount, meaning how much do I start with? Well, I deposited $500 in, so P is going to be 500. All right, my rate, R, my rate of interest is 6.75%. Remember, we've got to write this not as a percentage, so 6.75 divided by 100%, or moving this decimal point to the left 2 spots, R is going to be 0.0675. Now, T here, though, this is unknown to us. T is the amount of time in years it will take to reach whatever A is, in this case 1,000. That's not given to us, so it sounds like we're solving for T. Let's go ahead and plug these things in. 1,000 is equal to 500 times e to the 0.0675, and I don't know what t is, so t. Okay, let's solve some things here. Let's try to get this e to the 0.0675t by itself, dividing both sides by 500. All right, let's write it this way so it looks a little bit nicer. E to the 0.0675t is equal to 1000 divided by 500, that's going to be 2. Well, now this is just like one of the problems that we worked on earlier. I've got e to some power, and what I need to do is get this some power, okay, down to the main line here, getting rid of this e. Well, how I can do that is I'm going to take both sides to a logarithm. Since this is e to some power, I'm going to do the log base e of both sides, or in other words, the natural log of both sides. So the natural log of e to the 0.0675t, this is equal to the natural log of 2. All right, the natural log and e, these will undo each other. This will leave 0.0675t is equal to the natural log of 2. To solve for t, we are going to divide both sides by 0.0675, leaving t alone. So divide this side by 0.0675 and divide this side by 0.0675. What do we get? T is equal to, let's bring a calculator over. The natural log of 2 in the numerator. And the bottom is going to be 0.0675. T is roughly 10.27, we'll round that up, 10.27 years. In order for your money to double from $500 to $1,000, in this account, it's going to take about 10.27 years to do it. Hopefully this gives you an idea of how to solve exponential and logarithmic equations, as well as at least one real-world application for this.